In this course, there are three functional groups in hydrocarbons that you need to know. You need to know about the alkene functional group. The alkene functional group features a double bond, which must be between carbon atoms. And we know that carbons have 4 bonds, so these carbons have 2 other bonds each that could lead to other carbon atoms, to hydrogens, it could lead to anything. But as long as we see this pattern, C double bond C, it's an alkene functional group. The alkyne functional group is a carbon to carbon triple bond. Then the other bond can go to a hydrogen or to another carbon and continue with more of the molecule. But anytime you see the C triple bond C, the triple bond between carbon atoms, that is an alkyne. And we also have the aromatic functional group. The aromatic functional group has the delocalized pi bond, and it can exist entirely on its own as a benzene. Benzene is the simplest aromatic, but as a functional group, it would be attached to something else. And at the end of this bond, we could have 1 or many more carbon atoms. We could have many other things attached to this. 6 carbons with a delocalized pi bond, but on each of these carbons there's a hydrogen I could take off, and many other things could be bonded to it. But anytime we see this pattern, or the older version, the old-fashioned version, which is to represent every second bond as a double, anytime we see this pattern, it's an aromatic functional group. In this course, there are 6 functional groups that have only oxygen. So there are 2 patterns here that are going to be very important, but it's also important to know where they are placed and if they exist on their own or with other things. So the first functional group is an alcohol. So an alcohol will have a C to O to H pattern. We know that carbons have 4 bonds, so there are 3 other bonds that could be to anything else. This is called a hydroxyl pattern, and the hydroxyl pattern alone is an alcohol, but it is also present in other functional groups. We have an ether. An ether features an oxy pattern, which is an oxygen that interrupts a carbon chain or ring. Whenever the oxygen occurs between 2 carbons, that oxy pattern alone makes an ether. So we also have the aldehyde and the ketone. Both the aldehyde and the ketone feature a C double bond O. But in the aldehyde, it must occur on a beginning or end carbon, a terminal carbon. That carbon can only be attached to a maximum of 1 other. There must be a hydrogen here. It must occur on an end or a beginning. It's terminal. If we have exactly the same pattern, but the carbonyl group, the C double bond O, is between 2 other carbons, then it isn't an aldehyde, it is a ketone. And ketones have the carbonyl group between 2 other carbons. In other words, the carbonyl group is interstitial, in between 2 others. We have the carboxylic acid functional group. Here we have both a C double bond O, a carbonyl, and an OH attached to a carbon, a hydroxyl. But although the hydroxyl alone is an alcohol, and the carbonyl alone is an aldehyde or ketone, when both the carbonyl and hydroxyl groups occur on the same carbon, it isn't either of these. It is in fact a carboxylic acid, its own functional group. Because it takes 3 bonds to make a carboxylic acid functional group, these are always terminal. I only have one other bond that could be connected to the rest of a carbon ring or chain. The final functional group with oxygen is the ester. An ester has a C double bond O and a single bond O, like the carboxylic acid, but unlike the carboxylic acid, instead of having a hydrogen in this position, it has another carbon. We can have any number of carbons in this direction or in this direction. But the pattern here is a double bond O, single bond O, and then back to another carbon. So the ester has an oxygen that interrupts a carbon chain, an oxy-oxygen, just like the ether. But in the ether, this pattern is alone. Here, the oxy is on the same carbon that has a carbonyl group. And the two together make it an ester. There are 2 functional groups with nitrogen you need to know in this course. In an amine, we have a nitrogen. If we have at least one carbon attached to the nitrogen, it's an amine. So the amine could have a carbon with an NH2. It could be an NH here, and I could have a second C, or I could even have 3 carbons. The only thing that's important is a carbon to nitrogen bond makes it an amine. Carbon to nitrogen bond makes it an amine, and that's all I have. The amide is very similar, but here the carbon to nitrogen also features a carbonyl group. On the same carbon that's connected to the oxygen, it needs to be a carbonyl group. So this carbon has 1 more available bond, and the nitrogen has 2 more available bonds. These can be to anything, so often this would be 1 or 2 hydrogen, but it could be bonds to 3 carbon here as well, and not have any hydrogen at all. So the amide has a C to N bond, but the C must also have the carbonyl group. There's another functional group that's very useful for you to know. It's not in the course outline. We won't test you on this directly, but we will talk about it when we go on to talk about polymers. And that's the alkyl and aryl halides. So alkyl and aryl halides feature a halogen. Chlorine, fluorine, or bromine, they have a halogen. Now the halogens in family 7 make 1 bond, so they can easily take the place of hydrogen. So all I need to do is take a hydrocarbon like CH4, and instead of having 4 hydrogens, I'll put in X, where X represents a halogen. It could be chlorine, fluorine, bromine, etc. It takes the place of a hydrogen. That would be an alkyl halide. I say alkyl halide if it occurs in an aliphatic, an alkane, an alkene, or an alkyne. Or aryl halide when I have the same thing in an aromatic. So for example, this is an aryl halide. People also call them haloalkanes, haloalkenes, haloalkynes for the various families. Chlorofluorocarbons are various names, but we'll just stick with alkyl and aryl halide.